Hello, statistics students. Today is another incredibly cold day in the Ozarks. The university has canceled classes because it is just too cold. The snow is blowing, and you do not want to be outside, even with a fur coat on. And if you do go outside, you want to get back inside as quickly as possible. Bring in the brass monkeys, because the polar vortex is streaming all over us. The snowdrifts are making it hard to even get up the stairs. Today is a good day to get yourself inside, curl up with somebody warm, and let's learn about business statistics. Well, I'm your instructor, Dr. Todd Daniel, and this is week 6 of Basic Business Statistics. We're going to get started this week talking about describing distributions. And for that, we will use a description of skewness, kurtosis, modality, and z-scores. Joining me this week is Mickey. He's ready to go to his office, so I'm going to make sure he's in place, and then we're going to get started describing distributions. Mickey is in his office, so let's get started talking about distributions. The most important distribution in all of statistics is the normal curve. And one reason why the normal curve is so useful to us in statistics is because so many things in nature form up into a normal curve, such as height. So imagine that it's a warm spring morning, there's no snow, the weather is beautiful, and we invite all of the students to come down to the football field. And on the football field, on each of the yard markers, we've placed a sign that indicates a height ranging from 5'0" to 6'6". And we ask each person to go stand one behind the other behind the sign that best represents your height. So you know how tall you are. Go stand in the line for your height. Then we go up to the reviewing stand and we look out over the football field and we're going to see a distribution. We're going to see more people in some lines than other lines. And what we will also see is a normality of that distribution. More people are going to be in the line that is the most common or the mean score. So in statistics, we call this a normal curve. I want you to look at these bars in the histogram and imagine that those are people standing in line behind a sign for how tall they are. And the score in the middle would be the average score. In our example, it was 5'10", at least for the males. We could get rid of the bars and instead of the bars, just use the curve. And that is the normal curve. You notice we've removed the y-axis, just kept the x-axis. We just have this curve, and that curve represents frequency. Just the way that the bars do, number of people standing in line, that curve is just the smooth, ideal curve of frequency. Well, not all curves are normal, and we need a way of talking about non-normal curves. So what could happen with a curve? The scores could get bunched together, they could be spread out. That's called kurtosis. The kurtosis of the curve is describing how peaked or how flat that curve is. If all of the scores are tightly bunched together so that the score leaps up in the middle, right, the curve leaps up, that would be a leptokurtic curve. It's very peaked. You can think of the scores leaping up, leptokurtic. On the other hand, if there's a lot of variability and the scores have spread out, they've become flattened, that is a platykurtic curve. Think of plat, rhymes with flat, or plat like a plate. A low flat curve is platykurtic. Much more variability in a platykurtic curve than in a leptokurtic curve. Leptokurtic means low variability, platykurtic means high variability. Now there's another type of curve that we could talk about, which is the mesokurtic curve. That's a middle curvature. That would be emblematic of a normal curve. Well, let's practice with this for a moment. Look at this curve and tell me, is this mesokurtic, leptokurtic, or platykurtic? Well, clearly that is a leptokurtic curve. We can see how it leaps up in the middle. The second curve, however, is platykurtic. It's flat. And this third curve, well, that's a mesokurtic curve. It has a middle curvature. How about this curve? Well, that's also mesokurtic, but it's a little more platykurtic than the third curve. And this curve, wow, that's the most platykurtic of all of the curves. So what you can see from this example is we have the descriptions for platykurtic, mesokurtic, leptokurtic, and we can describe the relative amount of kurtosis, one curve being more platykurtic or less leptokurtic than another. So kurtosis is one way to talk about the curves. Another has to do with what we call skewness. In a normal curve, we have no skewness. The normally distributed curve, if we were to measure the skewness, has a measure of 0, and the mean and the median would be the same. In fact, the mean, median, and mode would be the same in a normally distributed curve. However, if the scores are pulled out to one end, we now have a skewed curve. If the scores are pulled out to the positive end, or to the right, it is a positively skewed distribution. The measure of skewness would itself be positive, and the mean would be greater than the median. On the other hand, if the scores are pulled out to the left, it is a negatively skewed distribution. The measure of skewness would be negative, and the mean would be less than the median. Now, you may recall an example that I gave you to help remember the direction of the skewness, which direction the tail is pulled out, and that comes from StatsCow, who reminds us that the skew is in the tail. You look for the direction that the tail is pulled out. Positive direction, it's a positive skew. Tail is pulled out to the negative direction, that is a negative skew. A third description of the distribution would be the number of curves in the distribution, which is a measure of modality. In a normal curve, we have just one mode, and so we would call that a unimodal distribution. However, in the example that we used last time of when is the best time to go fishing, we found that we caught the most fish in the morning and in the evening. That is a bimodal distribution. There are two distinct peaks in that distribution. What if we have 3 or 4 modes? That we call multimodal. We don't call it trimodal and quadrimodal. If you have that many modes in a distribution, something is really wrong in that distribution, and you need to stop, look at that data, figure out what's going on. Do you have overlapping distributions? What is really happening here? And you need to figure that out before you would use that in any kind of statistical testing. So we have unimodal, bimodal, and then multimodal distributions. Another form of a distribution could be if all of the scores are the same. Think of rolling a die. If you roll just one die, which is of course singular for dice, if you roll just one die, you will have an equal distribution of 1, 2, 3, 4, 5, and 6. That would be a rectangular distribution where every score has exactly the same frequency and there are no tails in that distribution. So I've now given you 3 visual interpretations of the distribution. You can simply look at the distribution and make a judgment as whether it's skewed or kurtotic or normal or has bimodality. But this next idea is a mathematical analysis, not just of the distribution, but of the scores within that distribution. And this is called the z-distribution. The z-score concept is this. A z-score describes how far a raw score falls from the mean in standard deviation units. So there are clearly 3 things that we need. We need to know the raw score, we need to know the mean, and we need to know the standard deviation. With that information, we can learn the relative location of any score in the data set. And this is also called a standardized value. In fact, we will use the standardized formula in Excel when we create z-scores. Well, I'm telling you about z-scores, but let me show you what a z-score actually looks like. These are z-scores. And you'll notice they all have something in common. They start with z, equal sign, and then either a plus or minus, followed by a 3-digit number, a leading number with 2 decimals. All of these are examples of z-scores. There are 2 parts to a z-score, the sign and the number. The sign tells you if the score is above or below the mean. If the z-score is positive, that is always above the mean. If a z-score is negative, it is always below the mean. And the number tells us how far above or below. It's the distance between the score and the mean in terms of standard deviation. Now the mean is 0. So if a z-score is a positive 1, it is 1 standard deviation above the mean. If it is a negative 0.32, it is 0.32 standard deviations below the mean. So at a glance, you can tell something about a z-score. There are 3 things that you should do. You should always include the sign, positive or negative, and the number. Always round to 2 decimals. And include that leading 0 if the value is less than 1. Look at these 3 examples, and let's figure out what they got wrong. In the first example, what did they get wrong? Well, they did not include the positive or negative sign. In the second example, what's wrong? Didn't include that leading 0. And how about this third example? Did not round to 2 decimal places. Now that we know what a z-score looks like, let's figure out how to calculate a z-score. This is the formula for a z-score. It is x minus the mean divided by the standard deviation. So remember, the z-score tells us how far a raw score, x, falls from the mean, x bar, in terms of standard deviation. X minus the mean gives us a distance. That's a deviation score. Divide it by the standard deviation. We have now put it in terms of standard deviation. Why do we need z-scores? Let's use an example. For this example, 3 men take a test of attractiveness, and they each score differently. Shifty scores 35, Mickey scores 65, and Antonio scores 90. And let me quickly add, Antonio, or Tony, was a student in a stats class years ago. And as I was doing this example, I was trying to come up with names for each of these guys, and he suggested we need to use, for the most attractive guy, it needs to be Antonio. And I said, okay, we'll use that. We'll go with Antonio. He said, no. You got to say it like you're Italian. Antonio. You got to put your fingers together. Antonio. So ever since then, I've used this Antonio for the most attractive of the 3 guys in this example. Okay, back to our example. What do these scores tell us? Alone, they don't tell us very much because we don't have anything to compare them to. What we would like to know, however, is the mean of this distribution, or the mean of this test. You see, if the mean is 10, then all of these guys are above the mean. And if the mean is 100, they're all below the mean. They're all below average. So what I do is I go back to the test itself, and I find that the average score on this test is 60. Now, I didn't get that from just averaging these 3 scores from the 3 guys. I got that from the test itself. It's a standardized test. Now that I have the mean of the test, I can compute deviation scores, x minus the mean. So Shifty, with a score of 35 minus 60, he scored a negative 25 as a deviation score. Mickey deviates by a positive 5, so we know he's above the mean. And Antonio got a 90, which is 30 points above the mean. Well, what do these deviation scores tell us? Well, that depends upon how close together or spread out the scores are on this test. So in order to compare these deviations, we need a standard to compare deviations. We need a standard deviation. The mean is the average of all the scores in the sample. Add up all the scores, divide by n. The standard deviation is the average amount of deviation. Now, we learned this last time. We had to jump through a few hoops to get there. We couldn't just average the deviation scores because they always average out to 0. But if you square them and then average them and then unsquare them, we get a standard deviation that we can use for comparison. Well, let's do that. I go to this test and I found that the mean was 60, but the standard deviation is 10. So we can now use the z-score formula, take each deviation score and divide it by 10. Remember, x minus the mean, which we've already done, is the deviation score. Shifty, with his score of negative 2.5, is way down here in the curve. He's toward the low end of the curve, 2.5 standard deviations below the mean. Mickey was close to the mean, slightly above the mean, and Antonio scored that positive 3. He was far to the right, to the positive end of the distribution. Remember, the mean is in the middle of the distribution. All of the scores, the frequencies of those scores are distributed. Well, this allows us to use something called the empirical rule. Now, you'll notice on this normal curve, I've added some proportions on the x-axis. The positive 1 standard deviation has a proportion of 0.3413, which we could also convert to a percentage. 34.13% of scores are between 0 and positive 1. Same thing is true for 0 and negative 1. Well, that means that 68% of the scores will be within 1 standard deviation of the mean. 95% of scores will be within 2 standard deviations of the mean, and 99% of the scores will be within 3 standard deviations of the mean. And not only 1, 2, and 3 standard deviations, 1.5 or 1.32 standard deviations also has a proportion associated with it. And we could use this to our advantage as we apply what we've learned from our z-score example. So for instance, how attractive are these guys relatively speaking? Shifty, with his z-score of negative 2.50, on the far low end of the curve, is more attractive than only 0.62% of all men. So we've used a z-table to figure out the actual proportion for a z of negative 2.50, and we can convert that to a percentage. Shifty, pretty low on that scale. Now Mickey, he's just slightly above average. His z of 0.50, more attractive than 69.15% of all men. But Antonio, he's an attractive guy. Positive 3.0, more attractive than 99.87% of all men. So truly a handsome gentleman. Here's looking at you, Antonio. Another important takeaway from this study is that half of scores are above or below the mean. So the mean of 0 is a proportion of 0.50. Half of the score is above or below. So that means that if we measure all of the students at our public school, half of them are below average. And of course, half are above average. And no matter how much money and effort we put into improving their test scores, half of them will always be below average. Because that is what the average means. Half of the scores will always be below average and the other half above average. Building upon the empirical rule, we need to learn about Chebyshev's theorem. This is Pafnuty-Chebyshev. And I'm certain that I'm pronouncing that wrong, but I have to say I love that name, Pafnuty-Chebyshev. Dr. Chebyshev's theory tells us that for any data set, at least 1 minus 1 over z squared of the items will be within z standard deviations of the mean. Now, this is true when the z is greater than 1, although it need not be an integer. So we could use a 1.23 or a 2.86. What this means is that for any distribution, no matter how skewed or kurtotic or non-normal, we will always have at least 75% of the data values within 2 standard deviations, 89% within 3 standard deviations, and 94% of the data values within 4 standard deviations. So again, this is different than the normal distribution. This is for any distribution. And we can therefore use Chebyshev's theorem to determine, given a mean and a standard deviation, what proportion of the scores must be between 2 given values in our distribution. We will now learn how to calculate z-scores in Excel. I'm going to be using the Dog Toys 2 Week 6 Excel file. Get that file open, and I will teach you about how to use the standardize formula to compute z-scores. Once the file is open, you will see on the first tab all of the data in the Dog Toys dataset. On tab 2, the z-scores tab, you'll see the layout for what we're going to do to standardize these z-scores. Now, the standardize function requires 3 arguments: the raw score, or x, the mean, and the standard deviation. We will be using the 2 scale variables in this data set, number of toys owned and days to failure of the gift toy. We need means and standard deviations, so let's create those first. In cell G4, type =, average, open parenthesis, B2. That's the start of the Dog Toys dataset. Let's make this an absolute reference. So on my Mac, I do Command T. On a PC, you would use F4. Colon, B51. And again, make this an absolute reference. Close parentheses and return. We've now created the average. It's a 6.08. Drag that formula down to the standard deviation. We've copied the formula, and let's just replace average with stdev.s. Now we have the mean and standard deviation for the toys owned. Let's do the same thing for days to fail. The mean is =, average, D2, absolute reference, colon, D51, absolute reference, close parentheses, return. Drag that down and change the second formula to stdev.s. Great. Now we have our mean and our standard deviation. We can compute the z-scores. Go to J2 and we'll create the z-scores for toys owned. Type =, standardize, open parentheses, and then click on B2, the first data point for toys owned, comma, and now we need the mean, which is in G4, make that an absolute reference, comma, the standard deviation is in G5, also an absolute reference. Close parentheses and return. We've created our first z-score. Now drag that z-score formula down the length of that column, and we have created z-scores for each score in the toys owned variable. Let's do the same thing for days to fail. In cell L2, type =, standardize, click on D2, comma. The mean is in cell G8, absolute reference. The standard deviation is in G9, also an absolute reference. Close parentheses, we've created our formula, and we can drag it down. As we examine these z-scores, we may notice some that are particularly large, and large z-scores indicate the presence of outliers in our data set. And we will learn next about what an outlier is and what to do about them.